Welcome back, everyone. We are to section 4.2, and we're going to be talking about partial derivatives. In the previous video, we talked about multivariable functions, meaning we have more than one variable to represent our domain. We're going to stick to z equals f as a function of x and y, just to keep it kind of simple for us. It can get much more complicated, but we're going to stay here. So the derivative, normally when we take it, there's only one variable to take it with respect to. Now that we have more than one, we have to specify. So if we take the partial derivative of f with respect to x, that means that everything else in the function is considered a constant. So if there's a y or a z or any other variable in there, those are all considered constants relative to the x direction. Same with respect to y. Only the y is active. Every other variable can be considered a constant relative to the function, to the variable y, I should say. And we have some new notation, and it's not totally accurate. So we have these as notations. Now, the denominator here should also be that weird looking d thing. It shouldn't be a regular dx for the Leibniz notation. And this is going to be easier if we just jump right on into it. So we have a function f of xy equals 6x squared plus 2xy to the third plus 5y to the sixth. And we're going to find the partial derivative with respect to x, which means x is the only active variable. So 6x squared becomes 12x. And because 2xy to the third, the x just becomes a 1, so we just end up with 2y to the third. And the 5y to the sixth is now a 0 because it's considered a constant relative to x. And when we go with respect to y, 6x squared is gone. It doesn't count. The 2xy to the third becomes 6xy squared. And 5y to the sixth becomes 30y to the fifth. And here are our two solutions for our two different derivatives in two different directions. For number 2, we're taking the derivative with respect to x. This becomes 4e to the 3xy. But when I do chain rule, with respect to x, that means derivative of x is just 1. So this just leaves me with a 3y left. So we end up with 12y e to the 3xy. That is my final answer there. And what we're going to do is, for this one, is we're going to take the derivative with respect to x. And remember, the square root means 1/2. And with respect to x, that just gives me a 10x. And that's going to clean up and become, now the 10 and the 2 reduce. I'm just left with a 5x over the square root of 5x squared plus 4y squared. So now when I plug in, x is -3 and y is 2. We get -15. Down below, we have 5 times 9 plus 4 times 4, which is 16. And I could get a decimal approximation or rationalize the denominator if we want, but I'm just going to leave it as is. It's totally fine as it is. Now for number 4, we have our Cobb-Douglas production function. P of Lk equals 30L to the 0.7 power, K to the 0.3 power. And the derivative of P with respect to L is going to be 30 times 0.7 L to the 0.7 minus 1, K to the 0.3. 30 times 0.7 is 21. This is going to give us 21 K to the 0.3 over L to the 0.3. And if we take the derivative with respect to K, we're going to get 30 times 0.3, L to the 0.7, K to the 0.3 minus 1. 30 times 0.3 is just 9. And this becomes K to the negative 0.7. There we are. So moving on to number 5. So an Oregon fiber manufacturing facility, an analyst estimates that the number of pounds of acetate fibers that can be produced is given by the function Z equals f of xy, 14,500x plus 4,000y plus 6x squared y minus 5x cubed. And x is the number of skilled workers, y is the number of unskilled workers. So for part A, they want us to evaluate f of 1948. It's going to be 14,500 times 19 plus 4,000 times 48 plus 619 squared times y, which is 48, minus 5 times 19 cubed. Let's see what we get. 1,500 times 19 plus 4,000 times 48 plus 6 times 19 squared times 48 minus 5 times 19 cubed. That's going to be about 537,173 pounds. Of acetate fibers. Find an expression f sub x, meaning the partial derivative of f with respect to x, for the rate of change output for skilled workers. Okay, so we're going to take the derivative of the function with respect to x only. That's going to be 14,500. 14,000y goes away, it's gone completely, plus 12xy minus 15x squared. And now with respect to unskilled workers, that's y. So the 14,500x is 0, goes to 0 when we take the derivative with respect to y. We end up with just 4,000 plus 6x squared. The y goes away. And the minus 5x squared also goes away. So we just have a smaller expression. Find the rate of change of output with respect to skilled workers when 19 skilled workers and 48 unskilled workers are employed. All right, so that means I'm going to take the answer to part B. Over there. Let's see what we get. 1,400. 14,500 plus 12 times 19 times 48 minus 15 times 19 squared. So I'm getting about 20,029 weekly pounds of skilled worker. And then we're going to do the same thing, except now with the unskilled worker. So this is going to be 4,000 plus 6 times 19 squared. $6,166 weekly pounds of unskilled worker. All right. Let me highlight the answers real quick. And that is going to do it for this section. Not too difficult. The next section's a little bit beefy, so we will get through it together.